My name is Shuji-oh. I'm a PhD student at the Nara Institute of Science and Technology. The paper I'll be presenting today is titled IVNPROTECT, Isolable and Traceable Lightweight Canvas Kernel-Level Protection for Securing In-Vehicle Communication. Recently, the number of wireless interfaces is increasing in vehicle, and it makes additional benefit for your comfort or driver assistance systems. But these interfaces also provide potential attack vectors for attackers. And this is not a hypothetical threat. An actual one was shown several years ago by researchers named Miller and Barasak. Next, we explain some features of CAN and its vulnerabilities. CAN stands for Controller Area Network. What was developed CAN protocol to simplify the wiring in vehicles. CAN also de facto standard protocol in vehicle protocol. CAN also has 4 features. Some researchers point out some vulnerability caused by the features. For instance, because of lack of sender ID and broadcasting, so receiver node cannot identify the sender node. And CAN has 64-bit data fields. So it means that adapting message authentication code is difficult. And CAN baud rate is 500 kilobits per second and bus topology. So CAN vulnerable is those attacks. CAN is vulnerable to those attacks. So in this research, we focus to research the prevention of those attacks. So therefore, some researchers proposed intrusion detection or prevention system as a countermeasure for these vulnerabilities. Here, we explain modern in-vehicle network and attacker model. First, we explain the modern in-vehicle network. So modern in-vehicle network consists in ECU and CAN and automotive Ethernet and IDS. ECU stands for Electronic Control Unit, which is a small computer in vehicle. ECU controls automotive functions such as motor or engine and so on. So by the way, because an attacker can intrude interconnected ECUs, like IVI, an attacker can also can send malicious data. For example, an attacker may send numerous messages to the network. So we assume that an attacker can send those attacks from internet-connected ECUs such as IVI. In this slide, we introduce the previous research and these issues. To protect the network from those attacks, Canary has been proposed. Canary can isolate a rogue ECU like a ECU2 in this figure by relay switching circuit. However, Canary requires hardware modification of CAN, so it makes it difficult to deploy Canary to the real-world canvas. So ID hopping mechanism is a moving target defense mechanism in CAN. It also requires hardware modification of ECUs because the ID hopping mechanism is provided by the CAN controller, which is CAN-specific hardware. So the ID hopping mechanism is also difficult to deploy. On the other hand, IDS side protection has been proposed. As one of the IDS side protections, frame corruption has been proposed. Frame corruption destroys a malicious message by sending the message at the same time. But frame corruption also occurs by ECU failure. So therefore, it is not possible to distinguish between frame corruption caused by IDS and ECU failure. Finally, we introduced ECU side protection. ECU side protection has the advantage of deployability because ECU side protection do not require bus modification like canary. As one of the ECU side protections, a hardware-based allow list has been proposed. The allow list can prevent those attacks with the highest priority ID in CAN. However, the allow list can be bypassed by those attacks with allow listed ID. To summarize, existing protections has three issues. The first is difficult to deploy the protection, which requires hardware modification. To meet the requirements, our proposed method provides protection with software layer. The second is untraceable for cause of isolation. To solve the issue, our proposed method sends a warning message by isolation of a rogue ECU. The third is incomplete isolation like allow list-based protection. To be complete isolation, our proposed method isolates the rogue ECU using a state mapping model called security error states. To solve three issues, we propose canvas kernel level protection called IVNPROTECT. We assume that IVNPROTECT is installed in Linux-based ECU. So IVNPROTECT is implemented into CAN device driver. So next, we explain the overview of IVNPROTECT. At first, IVNPROTECT receives the transmission request from user processes. Then two attack detection modules in IVNPROTECT monitors the transmission requests. If a transmission request is labeled as attack, IVNPROTECT determines sending or discarding the request based on security error states. Next, the next slide describes the two detection modules and security error states. Here we introduce the security error states. Security error states handles security errors such as transmission using not allow listed IDs or change of similarity in transmitted IDs. Once the security error occurs, IVNPROTECT transfers error passive state. And numerous security error occurs, IVNPROTECT transfers isolation state called burst-off state. Next is two detection modules. The first is allow list-based IDS. The allow list can detect transmission using not allow listed IDs. If allow list-based IDS detects transmission using not allow listed IDs, IVNPROTECT transfers the error passive state. And in this state, IVNPROTECT discuss messages using not allow listed IDs. In other words, in this state, IVNPROTECT only allow sending allow listed IDs. The second is similarity-based IDS, which is designed to deal with those attacks using not allow listed IDs. As with allow list, if similarity-based IDS detects rogue change of similarity, IVNPROTECT transfers the error passive state. In this state, IVNPROTECT inserts delay to mitigate those attacks. Here we elaborate on similarity-based IDS. Similarity-based IDS is a sliding window-based intrusion detection method. In the research of in-vehicle network security, it is the fastest DOS-attack detection method. Here we will explain how to detect DOS attacks. First, similarity-based IDs defines CIDs, which consists set of benign IDs. And receiving messages from the canvas, this IDs calculates the similarity. If the similarity is low value, this IDs regards as attack. In our IVNPROTECT, these procedures are conducted in kernel layer. So we installed Linux kernel into Raspberry Pi 3 Model B+, and we implemented IVNPROTECT to device driver in Linux kernel. And to emulate CAN messages sent by an ECU, we captured actual CAN messages from actual combination meta ECU. In our evaluation, we replay the actual CAN messages with Raspberry Pi 3 Model B+ as benign messages. After this slide, we explain the following evaluation metrics. We evaluated the prevention of DOS attacks using IVNPROTECT. We conducted two types of DOS attacks, malicious ID DOS and benign ID DOS. Malicious ID DOS is DOS attacks not using ID 0, which is the highest priority ID in CAN. The benign ID DOS is DOS attacks using ID 127, which is allow listed high priority ID. In the case without IVNPROTECT, both of the DOS attacks increase the bus load. In the case with IVNPROTECT can disable malicious ID DOS because malicious ID DOS is filtered by allow list in IVNPROTECT. Also, benign ID DOS slightly increase bus load because benign ID DOS is not filtered by allow list in IVNPROTECT. But we confirm that benign ID DOS is mitigated by inserting delay of IVNPROTECT. Next is the benign transmission loss rate. To evaluate the benign transmission loss rate, we conducted that an actual ECU with IVNPROTECT sends the benign messages and DOS attacks simultaneously. And we changed the transmission queue length of the CAN interface and measured the loss rate. We confirmed that the loss rate is 0% over 400 queue lengths of CAN interface. Next is benign transmission delay. This evaluation was conducted at the same time as transmission loss rate. Particularly, those attacks of 300 microseconds is an attack with the full transmission rate. In the case of sending benign messages and malicious ID DOS, it didn't influence the transmission delay of benign messages. In the worst case, IVNPROTECT makes the benign messages delay 333 milliseconds. Next, we evaluated the overhead with IVNPROTECT. We measured the transmission time between starting to send 1,000 benign messages and finishing it. As a result, we confirmed that the overhead with IVNPROTECT 9.049 microseconds. It meets the requirements of the in-vehicle real-time system. Here we discuss the traceability of IVNPROTECT. We explain traceability again. A rogue ECU with IVNPROTECT has to send warning messages before isolation. So the warning message enables the other ECUs on bus to trace the cause of isolation. Here we show the traceability of IVNPROTECT. From the evaluation, the benign transmission loss rate is 0%, and benign transmission delay is 333 milliseconds. In other words, after 333 milliseconds from starting those attacks, IVNPROTECT can send a warning messages at least once. So next, we measure the time until transferring to isolation state called isolation time. As a result, we confirm that if the threshold transferring to the isolation state is 32, IVNPROTECT can send a warning message at least once. In this slide, we compare the conventional methods and IVNPROTECT. First, we compare the implementation location. Our IVNPROTECT is implemented in software layer on ECU. So compared with conventional method, IVNPROTECT has low deployment cost. The second, we evaluated isolability of rogue ECUs. The hardware-based allow list bypasses those tags with allow listed high priority ID. On the other hand, IVNPROTECT can isolate a rogue ECU with security error states. Third, we compare traceability for cause of isolation. Frame corruption destroys our malicious messages by simultaneously sending messages from IDS. But frame corruption also occurs by ECU failure. So therefore, frame corruption has no traceability. And our IVNPROTECT can trace a root cause of isolation because IVNPROTECT sends warning messages before isolation. So finally, canary and hardware-based allow list deployment cost is high because it requires hardware modification. T-check is implemented in software layer on ECU as with IVNPROTECT. However, T-check requires trusted execution environment of ARM CPU architecture, so it also requires hardware modification of ECUs. Finally, we elaborate on the limitation of IVNPROTECT. If an attacker manipulates the similarity of those attacks without exceeding the benign range, IVNPROTECT misses those tags. However, the similarity manipulated those tags consist IDs assigned to an attacker ECU. So if the attacker ECU only has lower IDs, this DOS tags is low priority. So in other words, this low priority DOS tags is not harmful to CAN. To sum up, in this paper, we proposed a novel CAN plus kernel-level protection called IVNPROTECT. IVNPROTECT demands low hardware requirements and can isolate a rogue ECU with security error states, and can isolate a root cause of isolation using a warning message. For people who would like to check on our work, we released source code in GitHub at the following link, so please check it. Thank you.